Good evening, and thank you for joining us at the APS Medal and Society Prize ceremony. I'm Jonathan Bagger, Chief Executive Officer of the American Physical Society, and I am delighted to welcome you to this evening's event. Tonight marks the 7th annual presentation of the APS Medal for Exceptional Achievement in Research, the Society's highest honor. We are also pleased to honor the recipients of the Julius Edgar Lillienfeld Prize and the Georgie Valley Jr. Prize. The mission of the APS is to advance and diffuse the knowledge of physics, and each year the Society presents prizes, awards, and fellowships to hundreds of scientists. These scientists are selected by committees of experts from across our community. Each recipient has the great distinction of being recognized for excellence by their peers. APS honors both recognize and celebrate the people who advance and diffuse our science. Of the many honors we award, the 3 tonight are not restricted to any one subfield of physics. So receiving one of these prizes represents a truly outstanding accomplishment. Tonight's awards highlight a few of the different ways that scientists are advancing physics. For example, through research by early career scientists that can dramatically impact their field. Through research that is accompanied by lecturing, mentorship, or communication across a variety of audiences. And through major research accomplishments, typically over a lifetime, that have transformed physics and adjacent fields. I am delighted to recognize Jay and Mary Jane Jones, who are online with us tonight and whose great generosity made possible the Society's Medal for Exceptional Achievement in Research. From the very first medal, awarded to my thesis advisor, Edward Witten, to last year's medal, awarded to theoretical physicist Gordon Bain, this honor has recognized truly outstanding contributions to research. And as you will hear, this year's honor is no different. So thank you, Jay and Mary Jane. At this point, I will share with you the second APS Medal and Society Prizes documentary. For the honorees, we hope this short video will serve as a lasting memento of this occasion. And for everyone else, we hope it offers a glimpse into the lives of the people being honored here. Please take a look.
Major advances in science are rarely the result of a lone genius, but behind great achievements are inspiring stories of remarkable individuals. Since 1899, the American Physical Society has worked to advance and diffuse the knowledge of physics for the benefit of all. APS honors are how we, as a community of physicists, recognize and celebrate those who further this important mission through their work and through their lives. Early career scientists are a critical piece of our community. They bring new ideas and perspectives to the table, and sometimes even transform the direction of an entire specialty area of the physics discipline. The Georgie Valley Jr. Prize recognizes an early career individual for outstanding scientific contributions to physics that has significant potential for a dramatic impact on the field. The 2022 recipient is Andrew Lucas for pioneering contributions to developing the theory of hydrodynamic transport in interacting electron fluids.
It was a very specific sort of series of life events that turned me towards physics. In my junior year of high school, I participated in the US Physics Olympiad. After that experience, I sort of thought, well, maybe I should take physics more seriously. I really want to do physics sort of for a career. I had a pretty direct route. I knew that was going to be my major, and I took lots of classes. My undergrad mentor, Xiaoyang Qi, right as he actually got to Stanford, he really took me under his wing and advised me, and so that that was really meaningful. There was a emeritus professor, Sandy Fetter, who was looking out for me, trying to get me more involved in the department doing research. I think it was really in 2015 that myself, my advisor, and other groups sort of started to take the idea of electron hydrodynamics seriously. And all hydrodynamics is the theory of what happens when you take many, many particles, conserving these same quantities, and you allow them to interact and collide off of one another. And you ask what happens if you zoom out, and you look not at individual collisions, but at the macroscopic many-body dynamics as a whole. A good analogy to have in mind is that we don't fly airplanes successfully because we model each of the individual molecules of air that bounce off of the wings. Instead, we recognize that the air moves as this collective medium, and we only need a few things like density and temperature and velocity. And just knowing those few things is sufficient. Just like for the plane, we don't need to calculate what each molecule is doing. We can instead just calculate the collective fluid flow over the wings. Our inspiration was that the same thing would also be true in the electron fluid. You wouldn't need to keep track of every single electron as it bounces around inside of this crystal lattice of atoms, but instead you could just keep track of the collective motion of the electrons. Part of the joy in doing physics is that you don't have to know the details about how every single thing works, because with just a few of the building blocks, you can really piece everything together. I wouldn't describe sort of taking on challenges in physics as zero sum, like if you're not successful, then it was all a waste of time. I think that when you approach a difficult problem, it's often the case that even if you don't solve the original problem you were looking to solve, you've still learned a lot of really valuable things in the process. You can think of working in theoretical physics as sort of like hiking or climbing one of the mountains behind me, that you can kind of see your way up to the summit. Although maybe you can't see the summit directly, you just sort of know whether you should be going up or down. But there's many paths that you can take to get there. And many people, may reach that same place, but have taken different paths. Part of the joy in working on these problems has just been the ability to work with so many different types of physicists and interact with so many different types of physicists. To have them all come together to the same conference and talk to each other and share ideas, that's been the most enjoyable part of this.
Having a productive research career is itself an incredibly time-consuming endeavor. On top of this, some physicists go beyond their immediate research community to serve as influential mentors and teachers, or to reach the broader public as effective communicators. The Julius Edgar Lillianfeld Prize recognizes outstanding contributions to physics and exceptional skills in lecturing to diverse audiences. The 2022 recipient is Chang Jung for outstanding contributions and leadership in experimental neutrino physics, and for outstanding teaching and outreach, especially on the physics of sports.
I remember something like 6 years old, and I told the people that I want to be a professor. I'm not sure I knew what professor really meant, but you hear about things, and I want to be a professor. I grew up very poor. My family was very, very poor. The schools I went was very poor, so I didn't have so-called role models any. But nonetheless, I was sort of naturally got interested in, I think it's a lot of other human beings do, that origin of time, where's how time began, and about the universe and such. Still working on it. I don't think I have answered those questions. I really didn't have that kind of mentor when I was younger. However, I did have the people kind of indirectly, they didn't mentor me, but I get to know them. One person, he's arguably probably the best physicist in the history of South Korea. His name is Ben Lee. When I was a freshman in college, Ben Lee came to Seoul National University. He gave a colloquium, And that itself was just cool. So we were all kind of mesmerized about it. And then I had the pleasure of meeting Maurice Goldhaber. He is, I will say, another legend in our field. And Maurice Goldhaber is the first person who experimentally determined how long protons can live. I was very much got into this question about protons, does the protons ever die? And then that question is the one actually led to my current research about last 30 years. Neutrinos generally were nuisance background for proton decay search. But then we couldn't find the proton decay, so therefore we changed our attention to neutrinos. So one of the experiments I was heavily involved in, the Super Kamiokande, K2K, and the T2K, those are the main experiments. One of the biggest things was that we discovered neutrinos oscillate. There are three types of neutrinos: electron neutrino, muon neutrino, tau neutrino. One of those interviews I had with the LA Times, I used the knowledge of ice cream for neutrino flavors. Let's say your muon neutrino is chocolate ice cream, and then you make a chocolate ice cream, you throw it across the country, and then when you receive the other side, it turns into vanilla ice cream. This actually happens in neutrinos. We do many experiments, we make breakthroughs, we understand more things. However, I consider this is that we are, building little sand towers. Towers get bigger and bigger, but still, it's a long way to go. Physical sports, I offered in 2003. I know I will be studying and teaching physics all my life, but I have interest in arts and sports. And then I realized that everything what we do in the sports is essentially classical mechanics. What's the difference between four-seam fastball and two-seam fastball and changeup? Four-seam fastball is not only stays more straight, it actually goes faster. Now, four-seam fastball thrown with an underspin, it experiences something called a magnetic force, which lifts the ball from below to upward. And so magnetic force is compensating the gravity large extent. That's why ball does not drop as much as other balls. As you are better, when you see a 100 miles an hour four-seam fastball, it appears to you ball is almost rising. But that's an optical illusion because the pitcher mound is higher up, and then ball doesn't drop as much as other balls. As a lecturer, as a professor, the way I see it is that no matter what topic I teach, as you walk in the classroom, essentially you have to consider yourself as a performer. So you have to know the level of students and then how to get their attention. But most importantly, you need to able to convey the enthusiasm. And then students can see that. That is like pleasure. That's the really pleasure of his life as being a professor here. And that's the pure joy of being a professor. And in fact, it's joy of my life.
The APS Medal is truly the Society's highest honor. With this prize, we recognize an individual with research accomplishments, typically over a lifetime, that have transformed a field of physics or even multiple areas of physics. It is a celebration of those dedicated to scientific inquiry and the pursuit of knowledge. The APS Medal for Exceptional Achievement in Research recognizes contributions of the highest level that advance our knowledge and understanding of the physical universe in all its facets. The 2022 recipient of the APS Medal is Elliot Lieb for major contributions to theoretical physics, so obtaining exact solutions to important physical problems which have impacted condensed matter physics, quantum information, statistical mechanics, and atomic physics.
Well, as a kid, starting with about the age of 10, something like that, I became interested in doing experiments with electricity and also woodworking. Part of this curiosity was inspired by my uncle that I mentioned, who had this bookshop. He had a huge collection of Japanese prints, and I fell in love with these prints. When I entered MIT as an undergraduate, as a freshman, I wanted to be an electrical engineer. The reason I switched from engineering to physics was I fell under the influence of my freshman year instructor. His name was Matt Sands. The first thing you learn in physics is mechanics. And I just didn't get it. He was very patient. And he somehow felt that I was worth following. And eventually I did understand it. And he got me to understand that this was really a beautiful subject. And so I decided I wanted to be a physicist. Science is an international enterprise, and I saw it in several ways. And when I finished my degree, I decided I would go next to Japan. I learned Japanese and at least enough to get around. It was a wonderful, fantastic experience. Just after I got my PhD, I realized, I have to say this frankly, my thesis was not very good. It was okay. And I thought about joining the State Department as a scientific attaché, but I did not do this. Otherwise, it was just, I just kept going. Maybe I was not really any good at anything else. So I don't get discouraged. I just wait for the next tsunami to. Once in a while, one is lucky and one produces a really good paper, which you know is important, even if nobody else knows it's important. And there have been papers like the strong subadditivity of entropy. That's one. I worked for 2 years on that all by myself. The other was this ice problem. The other thing was the stability of matter thing and why that works. These were high points, really high points. The year in which I solved this ice problem was 1968. A water molecule is one oxygen atom and two hydrogen atoms, H2O. And the oxygen atoms in the ice sit at a nice lattice, which you can see and measure. The hydrogens don't. They're sort of wobbly. And this wobble never goes away. You can estimate that the number of configurations, number of possible states of the ice would be with all possible wiggles. That's the entropy. What remained to be done was to actually prove this. I mean, actually calculate this number. So the number of ways you can put in these hydrogen atoms in such a way that at every point where there's an oxygen, there are two on the close side and two on the far side. That's a tough problem. And I solved that. The answer was 4/3 to the 3/2. Incredible, because I did it on a weekend. You asked me how I felt, that's how I felt. If I could start all over again, what would I tell a young person at this age? I would say, don't give up. If you think you can do something, just do it. Physics is made up of many parts, as we've come to understand. It's not. It used to be thought that there's one genius who starts everything. It doesn't work that way, if it ever did. Physics is a big enterprise with many people doing various things, being held together by a common interest in science. And it's important to have scientific institutes like the American Physical Society that bring all this together and publish journals and so on. And bit by bit, these different pieces interlace and interlock and produce, at the end of the day, something that's of value to the common good.
Sincere thanks to our recipients for participating in the video. And with that, it's my great pleasure to introduce the 2022 APS President, Francis Hellman, to present tonight's honors. Francis is a professor of physics at the University of California, Berkeley, and former dean of the Division of Mathematical and Physical Sciences. She has appointments in Berkeley's Materials Science and Engineering Department and the Materials Science Division at Lawrence Berkeley National Laboratory. She served as chair of the 2022 APS Medal and Society Prizes Selection Committee. Francis, over to you.
Thank you, John, for that introduction. And it is my great honor to present these distinguished prizes on behalf of the American Physical Society. Very much wish we were doing this in person, but there we are. Tonight's first prize, the George E. Valley Junior Prize, recognizes an early career individual for an outstanding scientific contribution to physics that is deemed to have significant potential for a dramatic impact on the field. The prize was established in 2000 under the terms of a bequest by George E. Valley Jr. It carries a prize of $10,000. The 2022 Valley Prize is presented to Andrew Lucas, University of Colorado at Boulder, for pioneering contributions to developing the theory of hydrodynamic transport in interacting electron fluids. So congratulations, Andrew, and would you like to say a few words?
Thank you, President Hellman, the prize committee, and Georgie Valley Jr. for this honor. The American Physical Society gives out quite a few prizes recognizing the great intellectual diversity and broad accomplishments of our community. Most of these prizes go to scientists with multiple decades of pioneering work, and I'm very humbled to be one of the 3 awardees honored at this event, especially at my age, and especially given the substantial impact that tonight's other 2 awardees have had. I'd like to briefly acknowledge some of the many mentors I've had over the years. My undergraduate mentor, Yang Chi, my PhD advisor, Subir Sachdev, my postdoctoral fellowship mentors, Steve Kivelson and Sean Hartnell, and lastly, my Boulder colleagues who have helped me to set up a good group of my own. Thank you all for believing in me and giving me the intellectual freedom to grow to the fullest of my potential. And thank you all for your honest advice, which has been so valuable over my career. I aim to be such a mentor for my own students. Out of so many junior scientists who have made creative and impactful contributions to our field over the past decade, I'm really grateful that my contributions to electron hydrodynamics are chosen from them to be acknowledged tonight. And I hope that my work will continue to be viewed in this regard for many years to come. Thank you again.
Thank you, Andrew, and we are entirely confident that you will live up to the honor of this award. So it's a great pleasure to give this to you. Next, turn to the Julius Edgar Lillienfeld Prize, which recognizes outstanding contributions to physics along with exceptional skills in lecturing to diverse audiences. The prize was established in 1988 from a bequest of Beatrice Lilienfeld in memory of her husband, Julius Edgar Lillienfeld. It carries a prize of $10,000. The 2022 Lillianfeld Prize is presented to Chang Jung from Stony Brook University for outstanding contributions and leadership in experimental neutrino physics and for outstanding teaching and outreach, especially on the physics of sports. Congratulations, Chang. Would you like to say a few words? You are muted.
Okay. Thank you. First of all, I would like to thank the APS leadership, honors program staff, and the 2022 Lillienfeld Prize Selection Committee for providing me with this capstone moment of my career. I'm both immensely honored and humbled to be on the list alongside the truly inspiring and illustrious past winners. As my childhood dream was being a professor and a physicist, and this prize recognized accomplishment not only in physics, but also in lecturing to diverse audiences, for me, this is the ultimate prize for my career. In this regard, I would like to express my deep appreciation of Beatrice Lillienfeld for having established this prize. I would also like to thank Peter Stevens for nominating me, and then Takashi Kobayashi, Justina Wagota, Bedel Sajeh, Katie Ulkovich for their kind supporting letters. Even though this prize is given to an individual, I have no illusion that this recognition could have been made without the collective dedicated work of my collaborators in T2K, K2K, Super Kamiokande, Uno, Henderson Dussel, and Jung. I would like to especially acknowledge all the past and present members in the Stony Brook NN Group for their essential contributions to this recognition. I share this prize with all of you, and I am fortunate to have you as my collaborators. I would like to honor two great leaders in neutrino physics, the late Yoji Dozuka and Go Nishikawa, with whom I worked together on Super Kamiokande, K2K, and T2K. I also pay tribute to late Maurice Goldhaber, Jack Maberger, and Peter Paul, who are my mentors, kind supporters, and dear friends. Throughout my professor career, I have received warm support from the faculty and staff in Stony Brook HEP Group, Physics and Astronomy Department, and strong support from US Department of Energy. For my physics of sports endeavor, I acknowledge Adel Sajeh for his fruitful collaboration. I'm blessed with many friends and family around the globe. I'm saddened by the fact that both of my parents cannot enjoy this day with us. I hope that they were able to imagine a day like this, and then it gave them some warmth in their hearts. My brother and sisters are all suffering from illnesses in Korea, and I'm so grateful that moved by my sister-in-law, Chang's saint-like dedication to the care of my brother. Special thanks goes to Vivian for raising 3 beautiful children and supporting me for much of my professor career. My children, Dali, Navi, and Oli, probably deserve a larger portion of this prize as they assist in my writing, public lectures, and even choosing outfits. I deeply appreciate the love and support for me, and I cannot imagine my life without them. The families of Hongjin Lee, Aaron Evans, Fumigato, David Martinez, as well as my nieces and nephews have special places in my heart. I would like to acknowledge the neutrino social community and my friends in Argentina, Germany, Norway, Poland, Russia, Spain, Switzerland, the UK, and in New York. One day, when I was around 10 years old, I was walking back from school over a frozen rice field during a snowstorm. My fingers were blue, and my face and feet were numb. Fighting through the snow in the solitude, I looked up the hill where our lone small house was. There I saw my mom looking out of a small wooden window. In the end, we never walk alone. There is always someone thinking about us and supporting us. We should never forget this, and we should try to live every nanosecond of our lives together, caring for each other. Thank you all, friends, family, and colleagues attending. Love you all. Thank you.
Thank you, Chunky. That's a very, very lovely sentiments that you expressed, and it's a great honor to be giving you this prize. So finally tonight, I turn to the third prize. We honor the 7th recipient of the APS Medal for Exceptional Achievement in Research. The APS Medal recognizes contributions of the highest level that advance our knowledge and understanding of the physical universe in all its facets. It was established in 2016 with a generous donation from Jay Jones, entrepreneur. It carries a prize of $50,000. The 2022 APS Medal is presented to Elliot H. Lieb, Princeton University. Elliot is an accomplished mathematical physicist who has made lasting contributions to physics over 6 decades. He received his Bachelor's of Science in Physics from MIT in 1953 and earned his PhD in 1956 at the University of Birmingham, UK, in mathematical physics. Throughout his career, he has addressed important problems which require the development of new techniques and methods. A few of Elliot's significant contributions include exact solutions to several models, a proof of the Wigner-Yanessi-Dyson conjecture with implications for the strong subadditivity of quantum mechanical entropy, a proof of the macroscopic stability of quantum systems consisting of nuclei and electrons interacting via Coulomb forces, a model of Haldane conjectured integer spin chains with gaps, and identification of an upper bound on the speed of propagation of information in quantum lattice systems. These results have influenced the work of many scientists in condensed matter physics, quantum information, statistical mechanics, and atomic physics. Elliot has been recognized with numerous honors, including the APS AIP Danny Heinemann Prize for Mathematical Physics. He is a fellow of APS, a member of the National Academy of Sciences, and a member of several other international academies. On behalf of the American Physical Society, I am honored to present Elliot Lieb with the 2022 APS Medal for exceptional achievement in research, for major contributions to theoretical physics through obtaining exact solutions to important physical problems which have impacted condensed matter physics, quantum information, statistical mechanics, and atomic physics. Congratulations, Elliot. Would you like to say a few words?
Yes, I would. Thank you, Francis, for your kind words about my work. I am especially grateful to Jane and Mary Jones for generously establishing this prize and medal for extraordinary achievement in research. In this way, you have made an important contribution to a science that we loved for many years. Thanks also go to the prize committee that chose me for this considerable honor. I'm well aware that being on a committee of this type can be difficult and also time-consuming. I've been asked to say a few words about my work. My scientific life in physics has been centered on mathematical physics, which means the application of serious mathematical tools and ideas, such as functional analysis, to problems in theoretical physics. It means sometimes going outside purely physical boundaries and searching for definitive proofs of statements. Indeed, physics and mathematics are inseparable. Physics does not exist without experiments, and neither does it exist without the means to capture results in the form of clear, logical statements. A theorem is sometimes said to be the last line of a logical argument. It can sometimes be the last line of a theoretical physics argument. We don't always achieve such clarity, but I believe we should try. In any case, mathematics has a role to play beyond just calculations. A good historical example is Weil's and Wigner's profound development of group representation theory to understand atomic spectra. This was rare, however. I recall days when mathematics was a word to be avoided among physicists. But I can also say that attitudes are changing and have changed for the better. The old mantra, just calculate, is no longer the final word in theoretical physics. I have worked in several areas of physics. Some of the most important, as Francis mentioned, were the entropy of square ice, the stability of matter, Thomas Fermi theory, the Hubbard model and its Lieb lattice, density functional theory, the Lieb-Linegar model of bosons, the AKLT model, the Lieb-Robinson bound, the proof of strong subadditivity of entropy, the Lieb-Ingvarson axiomatics for thermodynamic entropy, the bound on exchange correlation energy, and the solution with Mattis of the Luttinger model. Except for the Luttinger model, I will not discuss any of these further, but I will illustrate my work by two brief stories which go back to my early days at IBM in Yorktown Heights. It was there that I found my focus in mathematical physics. My first story occurred in 1962, when Dan Mattis and I proved that Heisenberg's well-known theory of ferromagnetism, which is based on the exchange integral, could not be correct without significant modification. In fact, Heisenberg's theory is never correct in one dimension, thus strongly contradicting the belief that ground states should be ferromagnetic. One-dimensional ground states are never ferromagnetic, but even more, they are always totally anti-ferromagnetic. This theorem, which Dan and I proved, rightly shocked my former mentors Hans Bethe and Rudolf Peierls, who wrote about it in his delightful book, Surprises in Theoretical Physics. At that time, one dimension was supposed to be the prime example for the justification of Heisenberg's theory,
as Piles wrote in his classic book on condensed matter physics. Our surprise theorem was pure mathematics at work. It fully generalized to one dimension the well-known fact that the ground state of a helium atom with 2 electrons has spin 0 in the ground state, not spin 1. Here's the second story, this time about Luttinger's model. One of the heroes of modern mathematical physics was Walter Tyrring, a former head of the theory division at CERN, who made mathematical physics his main interest. In an effort to try to make field theory rigorous, Tyrring invented a one-dimensional, exactly solvable model in 1958. Many followers took up the challenge of understanding Tyrring's field theory model, and among other things, discovered bosonization rigorously within that model. Now, moving forward to 1963, 5 years later, Quinn Luttinger realized that Tyrring's model could be fruitfully adapted to condensed matter physics. Luttinger's model became quite popular and important, but unfortunately, Luttinger did not know about the intricacies of the Tyrring model that had been understood earlier, the bosonization work in particular. Dan Mattis and I, equally ignorant of that earlier literature, independently figured out bosonization and the correction to Luttinger's solution of this model. We did so while writing our book, Mathematical Physics in One Dimension. So we corrected what Luttinger was slight errors, and we published it. I would make 2 points here. The first is that mathematical physics is important for physics, but needs someone like Luttinger to be aware of it and make use of it. The second point is that it was a mathematical physicist, Tyrring, and not Tomonaga, who invented this popular model. Perhaps it should be most appropriately be known as the Tyrring-Luttinger model. Tomonaga had made heuristic and approximate calculations earlier, motivated by Bloch and by Thomas Fermi theory. But Tomonaga's work was totally unknown to Luttinger, who knew only Tyrring's work. Luttinger, by the way, was also a mathematical physicist, a fact not so well known. For example, in his study of Feynman integrals, he made deep conjectures about multifunction integrals, which he, Hermione Braskamp, and I eventually proved in a purely mathematical paper of broad interest, whose result is a contribution to functional analysis and is known as the BLL rearrangement inequality. That was a beautiful mathematical physics collaboration, and it is an example of physics feeding into mathematics. It's been a long road for me, and I want to finish by thanking the many people who helped me along it until I could find my own way. In particular, when I was a freshman student at MIT, there was Matt Sands of Feynman Lectures fame, who aroused my interest in physics, and there was Vicky Weisskopf. Then there were Rudy Piles, Jerry Brown, and Sam Edwards in Birmingham, UK. At Cornell, there was Hans Bethe. At IBM Yorktown Heights, there was Elliot Montrol, Ted Schultz, and Dan Mattis. And at Yeshiva University, there was Joel Leibowitz. The journey has been fun, with interesting twists and turns and full of surprises. Among them being the APS Medal, for which I again want to thank Jay and Mary Jane Jones, the Medal Committee, and the American Physical Society. Thank you.
Thank you so much. That was a remarkable, you have a remarkable history, a remarkable and distinguished history of accomplishments. And it's a great honor to be honoring you with this prize this evening. So with that, that concludes the presentation of prizes, and I will turn back over to our CEO, John, who will provide some brief closing remarks. John?
Well, thank you, Francis, and congratulations to Andrew Lucas, Chang Jung, and Elliot Lieb. APS celebrates your important role in advancing the physics enterprise. Thank you, too, to our guests for joining us to celebrate these outstanding scientists. Please join me in a round of applause for our honorees. Have a good evening and stay safe. Bye-bye.
Thank you.